to look at now is Chapter 5, Ideal Gases and Actual Gases. So the actual gases account for a non-ideal behavior of the ideal gas. The ideal gas law you're familiar with, and when we look at ideal gases, we're really looking at highly superheated vapors. So on the TV diagram that you grew so fond of in Chapter 4, we're really up here, and this type of place is where the ideal gases are. So it's really a highly superheated vapor that we're looking at. And so what we want to be able to do is model gas behavior, and the tables, because of liquids and vapors have very complicated modeling equations. Ideal gases have a very simple one, and the one that you're probably familiar with is the ideal gas law. PV equals N R bar T. And what we have is that we have kilonewtons per square meter times cubic meters, so that's the volume. Over here we have kilogram moles. We're going to have kilonewton meters or joules, kilonewton meters per kilogram mole, degree K, and temperature in degrees K. So both sides of the equation balance, and R bar is a universal gas constant. And so that means it's the same for all gases. So R bar is equal to 8.3143 kilojoules per kilogram mole, degree K. Now what we want to be able to do is, this is on a mole basis. So when you do chemistry, you typically have reaction equation, you have moles of this, moles of that. In engineering, we do things on a mass basis, so we want to switch from the mole basis to the mass basis. And to do that, we use the molecular weight. And so capital M for molecular weight is equal to mass over moles, or kilograms per kilogram mole. So if I look in table A1 on page 875, and you may want to pause the video and look in your book and see where table A1 is, because you'll be referring to it a lot. So it's on page 785. And I'm going to look up the value for air. So I'm going to look up the molecular weight of air. So for air, we have that M is equal to 28.97. And the first thing it says is pounds per pound mole. So I regret that I put that in there and didn't put in first kilograms per kilogram mole, or grams per gram mole. The molecular weight stays the same. This is just the number of pounds mass in a pound mole, the number of kilograms in a kilogram mole, the grams in a gram mole, and the number's the same. So 28.97 kilograms make 1 kilogram mole. And so if I want the individual gas constant, I divide the universal gas constant by the molecular weight. So R is equal to R bar over M. And so this is 8.3143. In our case, divided by 28.97. And we see that it's 0.287. If you look at the last column in table A1, you'll see that it lists the value for the individual gas constants in SI units. Now let's look at the ideal gas law, and we'll change it from the mole basis to the mass basis. So I have PV equals N R bar T. And what I want you to do is leave a little space here, you'll notice, so I could divide M over this. So Mn is equal to the mass, R bar over M is equal to the individual gas constant, and so I come up with that PV equals mRT. And we tend to use this equation a lot. If I divide by M, so I have V over M is equal to the specific volume, so I can write this on an intensive property basis, and I could have that PV equals RT. And what this tells me is that, and so this is handy to have as well, that you pay attention. So if I know any two properties, I can determine the third. Knowing any two properties, PV equals RT, finds third. So, for instance, if I have a tank, and the tank is 0.5 cubic meters, so we have a tank, P is equal to 500 kPa, it's going to be air, T is equal to 300 degrees K, and we want to find the mass, then the mass is equal to PV over RT. So it's equal to 500 times 0.5 divided by 0.287 times 300. Or we have the mass is equal to 0.29 kilograms. So I have what the mass is in the tank. And so this is using the ideal gas equations of state, and I have this version where I have mass, and this version where I don't. And basically if I look at this latter one, what you're doing is you're really describing a three-dimensional surface. So if I know P and T, I let this be V. So if I go in at a certain value here, I go up, and this gives me the value of V. And so that's what it's telling me. So it's giving me what that equilibrium surface is. I think trying to visualize things in 3 dimensions is a little tricky, and so I mostly recommend using the equations. You can recognize that this is what it's doing, but the visualization of this is sometimes tricky. So I wanted to look at a non-ideal gas equation of state and see how that compares to an ideal gas equation of state. So let's look at a non-ideal gas equation of state. And we'll use the van der Waals equation. There are many equations that we can use. So we have P is equal to R bar over T divided by V bar minus B minus A over V bar squared. And I just want to make sure you know what V bar is. So that's the specific volume on a mole basis. So if I'm looking at this V bar, I'm looking at P V bar is equal to R bar over T. So it's basically, it's the ideal gas law that we're using on a mole basis. And so what we want to do now, what do these terms mean? So what happens is that B accounts for the finite volume of gas molecules. And A over V bar squared accounts for the intermolecular forces. And so, if you remember where we had this TV diagram, and we started off here for the ideal gas, as we move down, the gas becomes more dense, and the molecules, there are intermolecular forces between them, and this is an attempt to have this account for this. Notice that if I get rid of the A and B, so if A went away and B went away, we come back with the ideal gas law on a mole basis. So all the ideal gas equations of state degenerate to or reduce to the ideal gas equation of state when you get rid of those terms. If we look at table 5.1, so if you look at table 5.1, it gives A and B for different gases. And so I need to be able to look them up in any case. So I sort of have this problem. I have to look things up to find A and B. So there'll be other ways that we're going to look at to model actual gas equations of state besides this. But it does require that I look things up. What happened for the van der Waals equation is that A and B can be determined in terms of the critical properties. So for van der Waals, there's a lot of tricky math involved, which is, to my mind, not worth the effort. But so we have 27 R bar squared times T sub C squared, the critical temperature, over 64 times P sub C, the critical pressure. Remember, I said all pure substances have a unique critical temperature and pressure, so we can find A from this equation, and we can find B from the following equation, R bar T sub C over 8 times P sub C. And what we want to do is, what I'd like to do is to introduce something that is a little bit easier to use. And let's see how that works. So we're going to introduce something called a compressibility factor. So if I start with the ideal gas equation of state PV equals RT, I have that PV over RT is equal to 1.0 for ideal gas. But if it's not an ideal gas, it will be equal to Z, the compressibility factor that is not 1. So I could have PV over RT is equal to Z, where Z is the compressibility factor, and it accounts for non-ideal gas behavior. So if I look at figure 5.5, and my drawing is not as good as the one in the text. And so what this does is it looks at the compressibility factor for nitrogen, and we're looking at Z. And so what we're looking at is what is the value for Z, and I'll have Z here of 1.0. And down on the bottom we have pressure in MPa, so this is our pressure. We have 1, 10, and upwards, 20, whatever. And so what happens for an ideal gas, so what we're interested in is what causes Z not to be 1. So if I look at a temperature of 300 degrees C, I'm going out 300 degrees C, I go out here, or 300 degrees K rather, 300 degrees K, and I have to get out to about 10 MPa before I get any deviation from the ideal gas law. So it takes a high pressure. We also can look, and you'll see there are drawings that look something like this, for 200 degrees K, and then here's the critical point. So this is the dome that we normally draw right side up, and we see what this is. So, when I look at this, air is made up of 80% nitrogen, so air behaves much the same way as nitrogen does. And nitrogen and oxygen are diatomic molecules, and they behave similarly in terms of their compressibility. And so what happens here is it takes a very high pressure and or a low temperature for Z not to be 1. So we need high P, low T, for Z not to be equal to 1.0. So we need that for nitrogen and for air. Now what happens is this was one for nitrogen, and so there were tables that were developed. People were able to get PhD theses and create different tables for different substances. But that's a nuisance. There could be hundreds of tables to look at. So what we have is something called a generalized compressibility factor. And here, what we're going to do is the diagram is going to look a little bit different. We're going to have to find the relative pressure and relative temperature. So we're going to be interested in P sub R, which is P over P sub C, your critical pressure, and T sub R, which is T over T sub C. In table 5.3, lists T sub C and P sub C. So if I go into table 5.3, I can find out what these values are. Figure 5.6 is the generalized compressibility table. Oops. I also uploaded one that's a little easier to use in Blackboard, so you can access that as well. And so, but we have that. So now what I want to be able to do is let's go in and I'll pick a couple of examples so we can see how to use this. So first, let me draw the generalized compressibility chart that we have in figure 5.6. I'll do a sketch of that here. You can look at it actually, draw your own sketch, look at the one on Blackboard, all are fine. So if I look at this diagram, we have here Z is 1.0, so I have this going across. And I have P sub R here, so I have P sub R 1, 2, 3, 4. So I have the value of P sub R. And what we also do is we want to be able to find TsubR. So the TsubR sometimes creates problems for people in terms of looking it up. So TsubR is something that goes like this. And this, it'll say 1.0, and this is TsubR. So it'll say 1.0, and that gives us what TsubR is. We'll have something that looks like this. It'll be 1.2. And so when you look, you'll see these curved lines look like that. And basically what we're going to do is go up in the following. So let me give you TsubR is equal to 2. TsubR is equal to 1.2. And now how do we find it? How do we find Z? So we go in at TsubR equals 2, and you go vertically upward until you reach the 1.2 curved line for TsubR. And then you go across and read Z. And in this case, Z is about 0.7. So if I look at that, I get Z is about 0.7. And that's how we use the diagram. And where I use Z in the ideal gas law, we have that P times specific volume is equal to ZRT, or P times total volume is equal to ZMRT. And so once I use Z, I can find the volume, I can find the mass. Mostly what this does is it affects the mass calculation because you have your temperature and pressure, so it's affecting the specific volume or the mass that's on. So now, let's look at the following as an example. So I'll go through a couple of examples so you can follow this on the chart, pause it, look these up yourself, see if you get the same thing. So let's look at air, and we have T is equal to 200K, so it's cold. P is equal to 7.5 MPa. T sub R is equal to 200 over 133, which is T sub C, and that's equal to 1.5. And P sub R is equal to 7.5 divided by 3.76 is about equal to 2. So if I look in the chart, so if I go in at 2 and go up to 1.5 and read over, I get a value of Z. Z is about 0.81. So you should see if you do this. And you notice there's some variability. If I get 0.81, you might get 0.82 or 0.8 or whatever. So it's not perfect, but it's close, and it does account for the compressibility. Now let's look at one, and let's take carbon dioxide. So now let's look at carbon dioxide. And I'll do the same condition. CO2, I'll have T is equal to 200. T is equal to 7.5 MPa. T sub R is equal to 200 over 304 is equal to 0.66, and P sub R is equal to 7.5 over 7.39. It's about 1. Is there a value for T sub R of 0.66? No. The lowest it goes is 1.0. So this shows that this condition, carbon dioxide is not a gas. Does not exist. All right, let's pick something that does. So if carbon dioxide didn't work, let's look at carbon monoxide and see what that is. So carbon monoxide, CO. Again, we have T is 200 degrees K. P is equal to 7.5 MPa. TR is equal to 200 over 133. Is equal to 1.5. P sub R is equal to 7.5 divided by 3.5 is equal to 2.1, and we get Z is about 0.8. So it's not that different than air. You'll see the molecular structure of these, of air and this, are the same. So for homework, 5.1, 5.5, 5.11, 5.17, 5.33. For 5.17, thermal equilibrium exists at all time, and what we have is we have an upside down can that's above the surface, and then so for 5.17, I have surface, I have a can that's filled with air, and then I push it down, and the air becomes compressed, and temperature is constant, or in thermal equilibrium, so that means it's constant at all times. And so we want to be able to evaluate that. So look at those problems.